Okay, let's go ahead and get started. Thank you everyone for coming to our final Boeing Colloquium of spring quarter. Today I have the pleasure to introduce Professor Jonathan Mattingly from Duke University. Jonathan has received a BS in Applied Math from Yale University and then went to ENS Lyon on a Rotary Fellowship. Jonathan then went to Princeton University to work on his PhD, where he overlapped with a young postdoctoral fellow by the name of Nathan Kutz. Jonathan then spent 4 years as a Sego assistant professor at Stanford University and 1 year as a member of the IAS in Princeton. In 2003, he moved to Duke, where he is currently professor of mathematics and statistical science. Jonathan is a recipient of the Sloan Fellowship and a presidential early career award for scientists and engineers. But I think that one of the most important things in that resume that Jonathan did was he was a lecturer for the 2016 Gene Golub Science Summer School on stochastic PDEs, of which I was a student along with a fellow UW alum, Don Rim. It was a great course that he taught that summer. Jonathan's expertise in long-time behavior of stochastic systems. It is an expert in the long-time behavior of stochastic systems. In 2013, as part of an undergraduate summer research program, Jonathan got interested in understanding and quantifying gerrymandering. His work in this now hot area is some of the first in mathematical sciences. Today, Jonathan will talk to us about this work. So please, everyone, join me in giving a warm welcome to Professor Jonathan Mattingly.
Thanks, Jeremy. Thanks. So I was told that if I'm up here, it's okay if I take my mask off. All right. Okay. I got lots of nods and thumbs up. It's like the schools are split in the world, whether that's the thing you should do or the thing you should absolutely not do. All right. So thank you very much, and it's a pleasure to be here. This is, like many of you were saying, this is one of the first people who have actually come visit. This is my first actual trip like this since it started. So what I want to tell you about is some work that my group has been developing over the last couple of years on how to think quantitatively about gerrymandering. I wasn't exactly sure how the audience is, but now that I see I'm on home territory, a bunch of applied mathematicians largely, I'll definitely make sure I hit the computational part in the middle, but there's some early stuff beginning to set the stage. So, oops. Let me see what happened. Okay, let's try again. Nope. Oh, there we go. It's working. Okay, great. So, what is this about? This is somehow about you have people who vote, and that's supposed to express their will, right? We wake up the next morning, the newspapers announce the outcome of the election, and we say, here's what the people thought, this is what they believed in, this is the policies they supported, right? So the people vote, they have an opinion, they express that opinion in the ballot box, and we get some results. And so, I see, maybe I'm too far away. There we go, okay, so I'm too far away. All right, so maybe I'll stand over here. All right, so we think of this vote as expressing the will of the people, and we think that that the results, though, I should think of as the interpretation of that will. And what's interesting about this whole process is that in the middle, here we have the map. It sticks itself in between the people actually voting and how we interpret that vote. And the point is, if you have lots of different maps, you actually can get lots of different voting outcomes. And this is not a fictitious made-up slide. I can actually make a vote that looks like the people on the left-hand side, and then you put them through different maps, and you end up with these different outcomes, right? And you can see that one of them is 310 for one party, the other one is 310 for the other party, and the other one is somehow split in the middle, right? And you can imagine what the newspapers read the day after this election is dramatically different when there's never been a single change in how people voted. All right? So, how do we choose this map? Because it determines so much, it's so important. I think it's important to think about how we choose that. All right? So, it's often done, and it's tempting to think about invoking external fairness principles. So you might say, proportionality. That's, you read the newspaper, they say, this many votes were cast. This many votes were cast for this party. This percentage was voted for this party, and this is the outcome. And then, depending on whether that's surprising to people, there's some commentary, right? Similarly, sometimes people want to invoke some idea of symmetry. We all love symmetry. You know, if this happens to you and then I'm in your shoes, the same thing should happen to me. Or some idea of efficiency. There was a lot of discussing at some point about efficiency gaps and how the power of certain groups. The problem is that while these might be all interesting ideas that we might aspire to, depending on what you think, it's not what our system was designed to do. So then to judge the system on whether it satisfies these properties is not really fair. So I want to separate two separate questions, and I want to make sure you understand which question I'm talking about mainly today. One question is, here's a set of rules, and you claim that these rules brought you to this type of map, which led to this kind of outcome. Is it true that those rules brought you to this conclusion? Alternatively, you can say, here was a set of votes, here's an outcome, do I like that outcome? Does that somehow fit with my idea of what a democracy is? How do I design the rules to make outcomes that give me the outcomes that I think fit with my perception of what a democracy should do, right? They're both really interesting questions. I am going to talk about the first one predominantly today. So it's not about whether it fits your expectations of what a democracy should do. I'm going to say, here are the rules that we have decided on. Was this implemented in a way, and the outcome was the outcome because of those rules or because somebody did something else? Because somebody put their finger on the scale, all right? So here, okay, so then that's not, so proportionality is not gerrymandering in some way, not what I mean by gerrymandering, or not being symmetric is not what I mean by gerrymandering, although I'll get to that a little bit at the end. If you look up the definition of gerrymandering, what it says is it says to manipulate or change the outcomes of an election, right? To make the outcome different by modifying the boundaries somehow. I put two words in red here, and that's because this somehow presupposes that you knew what the answer was, right? You're comparing it to something. And so when I first started thinking about this, that's kind of where I settled down on. The thing we really didn't understand was what the null, this is supposed to be some reaction to violating the null hypothesis, violating, what we thought should have happened. And how do we test that if we don't know what we thought should have happened? All right, so in other words, what would have happened without any political agendas? All right, so implicit in this is this idea of comparing to what would have happened. All right, so let me take a small detour and maybe try to motivate why you might want to care about what I'm saying. So these are the court cases that my team has been involved in, and this has actually led me to testify in court on a number of occasions and write briefs for the court, both as expert reports that were entered into court or sometimes amicus briefs to the court. And I mean, so some of the earliest ones are in 2017. This was Common Cause v. Rucho that went all the way to the US Supreme Court. Then there was Common Cause versus Harper, which eventually led to the revoking of all the maps in North Carolina for the 2020 election. So they were eventually overturned and replaced with new maps. And then some of these are 2022. Just last Monday, the US Supreme Court chose not to overturn the ruling in this case, which was that overturned all three of the maps for this recent cycle, right? Every 10 years we redistrict in the 10s, the 20s, there's every year that ends in 0, right? We redistrict. We just did it in 2020, so in 2022 we're going to use new maps for the first time based on new census data. And in North Carolina, they overturned all the maps that were drawn by the legislature, who draw the maps in North Carolina. Every state's a little bit different, so mileage may differ. And I've looked at lots of different states, but I'm going to largely, although we've looked at Maryland and Pennsylvania and other states, I'm going to largely talk, and Georgia is coming. We're going to mainly talk about North Carolina today. All right, and I shouldn't say that we're the only people who've done this. There's been a number of groups. I guess the other really group that's had a big effect historically, the earliest work also was Wes Pegden and Alan Fries and Maria at Carnegie Mellon. They've done some really nice work in a different but complementary direction. And then the metric gerrymandering group at Tufts has also done some work, and now they've started testifying in court most recently in these recent cycles also. All right, so what I'm going to talk about is I'm going to propose a method for assessing fairness, which combines some conceptual framework with some computation to make the implementation feasible. And I think what's interesting about this question from an applied mathematics point of view is that kind of letting yourself have the freedom to say, part of this problem I'm not going to actually be able to solve. That brought us to a point where we could have a different conceptual framework to evaluate fairness than people had used before. And then we reduce this to a computational problem that we then have to solve. All right, and I'm going to talk about both parts of that today. All right, and that's both of what we brought to this conversation. And I should say there's also some political scientists who had some similar ideas just a little bit before us in a different way, but Joey Chen and Jonathan Royden at Stanford and University of Michigan. Okay, so kind of the flow diagram is the following. We have some policy guidelines and laws. We're going to observe the implications of those rules and then observe maybe the relationship to our values. And then we'll critique the implementation in a particular case. And only then are we going to go back and look at what society's expectations were. Right? So we're not going to evaluate we're going to really evaluate a map on whether it correctly implemented or whether it did in an unbiased way implemented the rules that had been put forward. All right, so here we are back to this. So what is the basic idea that we're going to use? The basic idea we're going to do is we're going to draw a bunch of maps that follow these criteria. And so here I've listed a bunch of typical criteria. So some of the most basic nonpartisan criteria that people use when drawing maps is they want connected districts, they want compact districts, they want districts that are roughly equal population so that every representative represents roughly the same number of people, one person, one vote. Depending on where you are and what the situation is, you may have to satisfy some Voting Rights Act obligations. You may need to preserve certain municipal entities like county boundaries or city boundaries. And these are all different states, different rules about this. And some districts, people also want to protect incumbency courts. So some of these are a little bit more political than others, but the ones on the far left are the least political, and they're definitely nonpartisan. So you want to ask, what would you see? That's what we're going to do. We're going to ask, here are the principles we need to use to draw maps. And now we want to compare here. So let's just start for a second. So often when I've given this talk, sometimes I've done a little bit of, which of these is not like the other. So you can pretend for a second which of these was not like the other. And I think if you're honest with yourself, you'll decide that this one and that one are the same, and this one is different, right? If you just looked at them. But what I want to tell you is that these two maps are essentially identically politically, and this map is different. Right? And so that goes already to the point. Gerrymandering is not about strange-looking districts. They make good coffee cups and good T-shirts and make good late-night comedian, But it's really not the core idea of what's about gerrymandering. I mean, look, if you're trying to decide if somebody broke into your house, the fact that your front door is kicked in is a good indication that happened. But it's not the only way that your house can be broken into. So you can't just go around looking for front doors that are kicked in. That's not sufficient. All right, so the basic idea of what we're going to bring to this conversation is we're going to say, let's compare a bunch of maps. Let's compare a bunch of maps and see how typical a map is relative to what we would see if we made a bunch of nonpartisan maps. So here's 4 maps, historical maps in North Carolina. So you could look at them and start comparing. And maybe you could start contrasting them and looking at how they behave under different situations. And there's those 4 maps. Now, maybe it'd be helpful if you had a few more maps to compare. And of course, if a few is good, even more is better, up to a point. So what we're going to do is we're going to create an ensemble. We're going to create a statistical ensemble of maps drawn from a certain distribution. So kind of the main topic of conversation is going to be we're going to place a probability distribution on the space of redistrictings that are concentrated on maps that embody certain nonpartisan criteria we care about. The better they embody that, the better, more heavily weighted they'll be on our ensemble. And then we'll use some computational methods to sample from that collection to create a bunch of maps for comparison. And then we'll compare to those maps and see how typical or atypical they are. All right. So just as an example, here was a map used in the 2016 elections in North Carolina. There it is. And here's the voting pattern in North Carolina. It's kind of a low-resolution image, so it's a little bit bled out here. But you get the idea. It's a very purple state. It's mixed. It's more purple than this. The brown is actually different shades. It seems to be heated up. And so this map, if you use this set of votes with this map, you get this delegation. Okay? And that's the actual delegation that went to Congress. And so 3 Democrats were elected, yeah? So I'm sorry to insult you, but I just want to make sure you understand what I'm talking about because this is the point. So the point is that I'm keeping the votes the same and I'm changing the map. Right? And now I get a different outcome. And I keep going, and I keep going. And if I keep doing this, eventually this thing starts to stabilize. And so this is a very high-dimensional sampling problem. And when it starts to stabilize, then I know that I've kind of sampled enough maps, and I'm in a good shape, and you can do that adaptively, and we've done that adaptively in certain settings. And then you can say, okay, if I just use these nonpartisan criteria, this is the distribution of outcomes that I typically see with this one set of votes, right? No one's vote has changed. There's not been a ballot box stuffed. There's not been anybody whose votes were removed. No one, all the things people talk about a lot, none of that happened. We have one set of votes, it's done. But this variation is just due to how you drew the map. So how you inserted that conversation of interpreting the votes that were cast. Right? And so you see that there's a huge amount of variability. Right? You can go from 3 to 8. Right? Imagine the headlines the day after that election when 8 people are elected to one party or 3 people are elected to that party. Right? But the people's opinion didn't change at all. So you see how powerful the inserting yourself into this process is in the conversation. All right. So there you go. That's an actual election. Those were the maps we used in that election. Those were the maps that were used. After the court case threw out those maps, these were the maps that were used. If we had used those maps in this election, this would have been the outcome. So after the court case that we testified in, that my group wrote a report for, the resulting map changed it. And you might say this is an improvement, right? Here's another set of votes, same maps. This judge's map was not, I should relabel that now. It's a bit old, this labeling for this slide. This was a bunch of retired judges who pretended they were a nonpartisan redistricting committee and redistricted, half Democrats, half Republicans. And they redistricted, and this is what they made when they made their map. So their maps are actually pretty good. And the remedy maps that the court brought in are also pretty good. And these were the maps we used in North Carolina in 2012, and these were the maps we used in North Carolina in 2016. All right. So part of the story here is if you look at just one election, it's not enough to say, I want to make sure you don't leave here thinking like you look at one election, that's the answer. It's gerrymandered or not. It's really important. Each of these different elections can be thought of as a different probe, a different set of plausible historical votes that can use to probe structure the map. And what this shows is, here's a whole bunch of elections. Governor 2012, US House 2016 President, US Senate, Governor, North Carolina Secretary of State. This is the Democratic vote share statewide. And not surprisingly, if you get more votes to one party, the histograms, which are the outcomes of this ensemble of, 40,000 maps, 30,000 maps, something, 20,000 maps, I think in this case, actually. You see it elects more Democrats, right, as they get more votes, right? Not surprisingly, this histogram shifts to the right. And the remedy map follows that histogram to some extent, and the judges one does. Now, notice what doesn't happen with the maps we used in 2016. These purple dots barely move at all, right? So in some sense, I would say that, regardless of what you think about who won how many votes, this map fails the simplest test you could expect of a map in a democracy. The minimal test being, in a democracy, if people change their opinion, the people elected should change. Right here you have a dramatic swing from 45% Democratic all the way up to sometimes 52% Democratic, and it never changes the outcome of the election. The same people win no matter what. It's almost like you didn't even need to hold the election close, with like one exception, right? You didn't even need to hold the election. The results were foregone. conclusion. Right? So this is kind of non-responsiveness. This is insensitivity to the changing will of the people. The people change their will and the outcome doesn't change. So one of the conversations which I brought up today when I was talking to some of the students in the science chapter is, there are three parts of this. There's how do you mathematically interpret the policies and the laws to build a mathematical model? What computational methods do I use then to solve that problem? And then how do I find out what's going on in those maps? And then even more, how do I explain them to a general audience? Right? And so one of the most effective ways I found are the following movies. So what this movie is going to show is this democratic seat. This is a set of elections that have been created by shifting a voting pattern, spatial voting pattern, so that it starts off at 42% Democrat, and it's going to grow all the way up to something like 57% Democrat. And as that number increases, you're going to see this histogram shift to the right, because as more people vote Democrat, more people will be elected Democrat. And then the thing to watch is what happens. Right now, you look at this and you go, well, the enacted map is not so bad. Right? Here it is. Wow, it's not the peak, but okay, it's not the peak. There's some externalities. That's fine. But now let's see what happens. Here it goes. So the enacted map is not moving. Still not moving. The remedial map. And the remedial map is starting to move. Oh, there it goes. Yeah, the remedial map is tracking it a bit. Oh, there it finally moved a little bit. So it wasn't almost till 53% that the enacted map moved at all. From 42 to 53%, it never moved. Right? That's dramatic. That's a dramatic insensitivity. Here's what happens. So now this is the North Carolina General Assembly, the House. We have a bicameral General Assembly. That means we have a House and a Senate. Like most states, I think there's one state that doesn't, Nebraska. I forgot which one. I guess Nebraska has only one chamber. 120 seats. These lines are important because this is where the supermajority, if you have this many seats, you have a supermajority. You can override the governor's veto at will. And so it's just a fact that over the last decade, the governor has regularly been Democratic and the legislature has always been Republican, where a decade before it was the opposite, in fact. Here's the 50% line. This is when the power of the chamber switches, and then this is the supermajority on the other. So I want to show you how these maps, in some ways, as this percentage increases here, it shifts and this thing starts to shift. But what this overturned map, that was the map we actually used in the election. This is the map that was replaced from the courts. You'll see this starts to stick here. Right as this starts to transition here, this starts to become abnormal. It sticks just right around, and depending on the election, it'll actually stick on the other side of the supermajority. But only when they start to lose. Pretty soon, this will actually move completely to the other side of the majority line, but this line will stay to the far left. Right? See, most of the maps are giving the majority to the Democratic Party, and finally, there it switches. Right? And so these movies have been incredibly powerful to explain to the court what's going on. And so I don't try to make a specific statistical test. I believe that visualizations are really powerful. And so what I want to do is I want to show the court what's going on. Here's the structure of the map. And then let them put their own values about what the law says, about what the public policy is, and what the intentions of the Constitution of North Carolina are. And one of the reasons you may ask, why is this happening in federal court, in state court, not federal court, is because the state Constitution of North Carolina has a little more structure than the federal Constitution. In particular, it says that there's I forgot the exact language now, but basically elections should be fair. The federal Supreme Court doesn't, the federal Constitution doesn't ever say that, actually. Something to think about. So here's that same kind of movie again. And that's the same movie we just showed again for a slightly different election. And here is kind of a version of it using different elections. And you see that down here, the outcomes are rather typical. But as you start to cross over the supermajority line or get close to the majority line, all of a sudden the purple dots are again far to your left, right? They're dramatically under-electing Democrats. And I should say, we've done analysis of Maryland, and I can tell you a different story, but one that why the Maryland maps are essentially designed to protect incumbents, but to the advantage of the Democratic Party in Maryland. Okay. So now we're getting a little closer to up to date. This was the court case. So this is what I spent from November till sometime in January working on this year. We had an incredibly compressed schedule. Greg Hirschlag and I, who is my main collaborator, and I had to basically put a report together and turn it in on the 23rd of December after starting it somewhere in November. And then we had to put a rebuttal reports in 5 days later on the 28th of December. And then on the 31st of December, I was deposed under oath. And then on the 3rd of January, I was in court testifying. And on the 6th of January, I was called back as a rebuttal witness in court. So it's kind of a different kind of applied math maybe. And this is what the maps that were overturned in the end were. Let me go ahead and start these maps. You can see them going. So you're going to see the same kind of thing. This is the for the federal House of Representatives, and you'll see the same kind of behavior. They lag dramatically behind. And here you see the same thing. As it starts to become more democratic, this sticks for a tremendously long amount of time. All right? And it's this kind of non-responsiveness that we're registering and we're trying to explain to the court. And if you read the language, we've actually been able to change the language to talk about non-responsiveness. That's been picked up now. And when I first started this in 2013, 2014, there was a little bit, Joey Chen was testifying sometimes, but it was still not that accepted, these kind of simulations to express this. But now both sides have different witnesses explaining simulations and showing this type of modeling. Yeah, please. Yeah, I mean, but that's a choice you might make if you were in charge of making this maths. When you get a huge fraction of votes, you might be willing to give up a seat or two, because you already have a pretty strong majority, as long as you got those seats when it was close, right? And that's what happens here. And often, 58% is a ridiculous thing. That never happens in North Carolina. North Carolina is like between 48 or maybe 47 typically, and maybe 52 or 53, right? So that's out of play in some sense. And so this is an analysis we did at Wisconsin for an amicus brief we sent to the Supreme Court. And we saw the same kind of thing. We see that, this is Republican seats now, and you see the same thing, that when the Republicans are doing well, it's very typical. It's only when they're in danger of losing the majority that it all of a sudden under-elects Democrats. So you can't just look at the top corner and say, lawyers always want to look at this and get me to say in court, 7 out of 13 elections were typical, so this was a good map, right? Half the elections it was good on. Yeah, but it systematically was bad on all the ones where your party was going to lose control. Right? All right. So up until now, I've just been talking about the seats, who won how many seats. And I want to make sure that that's not the only part of the conversation we're going to talk about. How am I doing? We're doing good-ish. All right. So I want to show you kind of a representation of the outcome of an election, which we found very useful. So what I've done here is this is the congressional race in North Carolina from 1 year, 2012, 2016 votes. There are 13 districts at this time in North Carolina. I've taken the most Republican district and plotted a point where what fraction of votes was Republican was Democrat in that district. So something like 47%. And here they are, all the way up to the most Democratic. So in other words, the most Republican was about 29% Democratic, 35% Democratic in these elections. The second most was, there you go, the most Democrat, right? And of course, dots above that dotted line elect a Democrat, and dots below that dotted line elect a Republican, yeah? That's what that says, yeah? And I've just put some box plots on. Unfortunately, this is kind of faded on this screen. It's really hard to see, unfortunately. There's some box plots here. Somehow the resolution is killing my image. And so these are our ensembles. So box plot, 50% of the maps were in here. And what you see is as you get up higher here, there's all of a sudden these green dots here that fall dramatically, not dramatically, they're on the edge. So these are the judges' maps. These are the maps that we liked. Let me show you now what happened. These were the maps we actually use. And you see what's happened is there's been a dramatic number of Democrats removed from the districts that were in play, and they've been put into the districts that were safe Democratic districts. So this is the idea of packing and cracking. And so this is a way to quantify and visualize the effect of what people call packing and cracking. In other words, Democrats have been removed from these districts that they could have won and been put in the districts they were guaranteed to win. All right? All right, and it's exactly these jumps here that lead to this non-responsiveness. You can almost think about shifting this whole picture up and down and asking when, if I shift it up 1%, 2%, down 1%, 2%, does a dot cross a line, this line? If a dot crosses this line, that leads to a seat flipping. So when you have a huge jump like this is a whole range of percentages that will lead to no change in the outcome of the election. And so this we called this the signature of gerrymandering. I mean, it may overstate it, but that's the idea. And I want to be really clear about something. I've been talking about responsiveness. Responsiveness and competitiveness are not the same thing. Competitiveness, if you say, so Arizona wrote in their constitution at some point that they want as many competitive districts as possible. That means you try to put as many districts right close to 50% as you can. The problem is that people change their mind, right? So now you have a little bit of a change of opinion, and all of a sudden, all those districts who are right close to 50% are all way below 50%. And 4 seats flip like that. What I claim would be better for us is to have responsiveness like this, where there's a gradual set of districts that change their opinion. And that's actually what we see when we generate districts using sampling, this measure put on the high dimensional space of nonpartisan redistrictings that only take into account the nonpartisan redistricting idea. We tend to see exactly the structure. I can't prove that. It's related to some kind of order statistic, but it's highly correlated. There's a theorem there somewhere if someone can prove it. Okay, and this is just to flog a horse. This is the stuff we submitted to the court in the last couple months. And this is the kind of evidence that we showed, again, this non-responsiveness that I already talked about. And now here's these histograms, and we see, again, the same exact behavior. These districts had many less Democrats than they should have typically, and these safer Democratic districts had many more Democrats than they should have had. Right? And that's what we were able to convince the court about in our testimony. Okay. And again, I'm just reiterating this point I already made, that somehow responsiveness is the minimal democratic fact of an election system. It should change its outcome when people change their opinion enough. And how do you decide what enough is? Well, you do sampling to learn what a nonpartisan map, what properties a nonpartisan map would have. Okay, so I didn't put anything about Maryland because I wanted to talk more about the math, but we could have talked about Maryland too. But and let me just make a few other small points before I switch to the math. So first of all, proportionality. We're not talking about proportionality. If we were talking about proportionality, the center of these histograms would line up with this black line. They do not. So we're not talking about proportionality. And people talk a lot about natural packing. That is to say that one party tends to live in urban areas, the other party tends to live in suburban areas. Here's Wisconsin. We actually quantified that effect. We said, what percentage did the Republicans need to get to win 50% of the seats? They only needed 46% here. They only needed 49% in that election. They only needed 47% in that election. I'm taking the middle of these histograms, yeah? But then you ask, with the map that they ended up drawing, is this arrow over here that says WI. So even given that natural packing effect, these maps were incredibly friendlier to the Republican Party than the maps if you would just based on what the effect of that natural packing. So you can separate these two effects using these analyses. Okay, so then you can also even start to look spatially and figure out where this affects, but I don't really want to talk about that. So I want to talk about this now. Take a little breath for a second. I talk fast. I'm from the South, but it's hard to figure that out given how fast I talk. So I want to talk about how we build our maps. So if you're going to generate maps, what you might start off doing is doing the most basic thing you would think. So what a basic Bayesian statistician would do, or a statistical mechanician. they would do Ising flips. This is Iowa, actually, 4 districts. That actually is Iowa. What you might say first is you might find the districts that are between 2 different colors, the edges, right? And then you would, so there's actually grayed out, there's a background graph here that you can't see, which is just the adjacency graph. Then you would pick one of these edges at random, and then you would flip the color along that edge randomly in one direction or the other. And that's what we did in the beginning for Rucho. We did this, millions of times to move the boundaries and have them evolve. We didn't do exactly that. We did something which I'll explain to you in a second. So then in 2018, 2019, the group at Tufts, so Moon Duchin, Daryl DeFore, and Justin Solomon, had a really nice idea. They came up with this idea that they called Recom, which had some origins and some other ideas, but it was really a nice idea here. And they said, okay, fine. So we have each of these clusters that induces some subgraph, yeah? We could take 2 of these districts, the orange and the green, and merge them into one district for a second. And then draw a random spanning tree, right? A spanning tree is a tree on that graph that has no loops in it and covers every vertex. So here's a random spanning tree. There are fast algorithms for drawing random spanning trees. Okay? Wilson's algorithm, developed by David Wilson, who was at Microsoft for many years here in Seattle, is one of the important ones. And then you can walk across this graph and find an edge which has a good population balance between the 2 sides. That's just a linear search across here because it's a tree. That's also efficient. It's like order n. And then there's a couple that you pick one of them and you cut it. And that gives you a new partition of those 2. And that turns out to be a nice global move, which is really great because now it mixes things much quicker. All right, so that has a lot of great properties. The problem with both of these ideas is that they're not what we want. We don't want to create random redistrictings. What we want to do is sample a distribution that we gave you based on the policymakers' choices. So we want to let the policymakers inform a choice of measure on the space of redistricting, and then we want to sample that redistricting. Okay? And so I really don't want to talk about generating random maps. I hate it when people say that. What we really do is we put a distribution on the space of redistrictings, and then we sample that distribution. All right. So here's kind of the loop, the outer loop. Define a distribution, build an ensemble by sampling it, and then engage around visualization and analysis of what we see in that sample. All right? So here's kind of the steps. So we first, just as restating what was just there with maybe some more words, encode the law and policy in a distribution on possible redistricting. Then we algorithmically draw maps using Markov chain Monte Carlo. In particular, we're going to use something either like sequential Monte Carlo or Metropolis Hastings. I'll tell you about that in a second. All right, so, oh no. Oh, that's so sad. Okay, there's some beautiful gray boxes around everything, and they're all gone now. So this slide is going to get digitally cluttered really badly in a second. So what we're going to do is we're going to create a distribution by putting a score function, which is how happy we are. Low scores are good. And we're going to exponentiate that. So we're going to create kind of a Gibbs measure. And this makes sense statistically because what we're going to do is we're going to create this score function as a sum of one that enforces population balance, one that enforces compactness, one that tries to not split counties, one that maybe enforces the Voting Rights Act, and other ones. Okay? And by having them independent like this is in some ways the minimum entropy measure that has these sufficient statistics, if you want to think about it that way. That you can actually get some mathematical reasoning behind making this choice. And so, for instance, here's the compactness score. So I take the isoparametric constant, the perimeter squared over the area. That's bounded below by 4 pi, 4 pi. And so I want to make that as small as I can because that tends to make it more like a circle. So political scientists reinvented this. They call it the Polsby-Popper score. It's actually the reciprocal of the isoparametric constant. But we look at the isoparametric constant because it's nice and additive, and we add it over all the districts. We also just look at the L2 norm difference between the population in a district and the ideal population, right? The total population of the state divided by the number of districts. And other ideas about municipalities and ideas of how many people are ousted from a district which contains most of the other citizens in their municipality, right? Trying to have some idea of keeping your cohort, your community of interest. So in Michigan, we're also thinking more generally about other kinds of communities of interest. All right, so at the end of the day, we have this measure right here. Oops, I just did it. We have this measure right here, and we want to sample this. So now we've reduced it to a math question. Given this measure on the space of graphs partitions into some number of districts, how do I sample that in an efficient way? Okay? Okay, so here's the Metropolis Hastings algorithm. All right, I'm so tempted to say, how many people, but I hate when people do that because it's not. So if you don't know what the Metropolis Hastings algorithm is, you should go home and read it on Wikipedia. Okay, I'm serious, actually. So it's a beautiful idea about how to algorithmically sample from any distribution you're given, with lots of caveats about when it actually works computationally. But in theory, it works rather generally. In practice, as always, it works when it works. And we understand somewhat. So the idea is the following, is there's an idea of detail balance. So if mu is the measure I'm trying to sample from, the probability of being in this state is the probability of finding myself in this state, the measure there, and then the probability of moving from state B to state A. That's the probability flux between these two different configurations. And if I'm in local equilibrium, that means that the flux is the same going back. That's detail balance. That's a sufficient condition to have this be the invariant measure, the statistical equilibrium of this algorithm. And what Metropolis Hastings does is it's a smart way of saying, oh, if the flux in my particular way I'm drawing these algorithms is too much in this direction, I should sometimes reject taking this move. And so what it does is it looks at the ratio of these two probabilities, the fluxes, and if it's bigger than 1 in the wrong direction, if it's less than 1, you sometimes ignore taking that step. You reject that move. That's the idea of Metropolis Hastings. And so what we do is we want to use these algorithms via the Metropolis Hastings scheme to sample well from the distribution we care about. But the problem is to do this, I have to be able to calculate the probability of going in one direction and the probability of going in the other direction. Okay, and the problem is that nice Recom scheme, it was hard to do that. It was not a computationally feasible problem to calculate the backwards probabilities. Okay, and there's some nice grayed lines here, but that's okay. So these are a whole bunch of algorithms that people have used. So here's what we used at the very beginning, which was simulated annealing, and the Recon algorithm and some genetic algorithms people used. The problem with them is they were just really random algorithms. They didn't sample from the distribution we wanted to. Simulated annealing is kind of on the edge because you can say it's close to the one you wanted to. So then there's measures that actually reversible Recom and single node flip. And now the thing that we're using now is we're using a multiscale Metropolis Recom sampling algorithm, so a multiscale method, which I'll tell you about in a second, with an idea of parallel tempering. Okay? So these are the computational methods we're using. All right, so let me tell you about metropolized forest recon. So that's what we developed, my group. So it builds on the previous idea, and what it says is, let me just try to make this clear. So here's that same picture I had before. What we're going to do is we're going to study it, but now we're going to take that same picture, but now we're going to change it so that we can keep track of these arrows going backwards. And what we end up doing is a very simple idea, which ends up having a real great effect. And there were 2 high school students who helped work on this with us over the summer and during the year. Not surprisingly, one of them just published an improvement on one of Brian Greene's papers recently, now that he's at Oxford as a math undergrad. The idea is we want to change the algorithms to calculating this backwards probability. So now this is the most mathy slide I think I have in the whole deck. All right, so I'll just tell you the point. Is the reason it's hard, so I want to calculate a forward probability, and that's going in this direction. And the problem is that it's a sequence of maps and deterministic and random maps. There's a many-to-one deterministic map. Then there's a one-to-many random map, a one-to-many, a few random map. And then there's a many-to-one random map. And of course, the problem is when you want to go backwards, these are all not that expensive. If you have to invert a many-to-one map, that's very hard, because you have to sum over all the possibilities you could have come from, right? And then that gets multiplied by this whole tree going back. And so what we did was we simplified this to where we eliminated this step, and this made it computationally feasible. Okay, it sounds like a trivial twist, but it was really a perspective change that let us use the previously proposed algorithms as a Metropolis Hastings loop, which was unknown how to do before. All right, now let me tell you about multiscale. All right, let me tell you about multiscale. So our graphs come with a natural multiscale structure. We have counties, cities, precincts, maybe census blocks. And so what we do is, so here's our graph geographically spread out. But what we do is we abstract that to, we want to have a multi-scale representation where when we keep an entire district whole, we just only represent at the coarsest scale. And then when we end up needing to refine a county, we actually keep a finer representation. All right? And so the way this works is the following. Here's this kind of multi-scale representation, only fine scale structure when we need it. What we do is we merge two districts. So we merge the green and the white district to this white district here. And now what we do is, okay, unfortunately, okay, there's a whole tree drawn here. So let me just tell you what's going on because it's not visible on this projector for some reason. So it's on my screen. I know speakers always say that, but it's true. So we draw a spanning tree at the level of counties. So we have a coarse level spanning tree. And then we choose a place to divide it. And then when we divide it, we then draw a spanning tree on the next finer scale with the right boundary conditions. And then we choose a place to divide it. And then we refine it. So we end up with a spanning tree that looks like this, where it's a coarse level object and then a fine object at the interfaces. And this kind of logarithmic scale up lets us do much bigger sampling problems than we could do before. And so in this most recent court case, we actually used this multiscale Metropolis Hastings forced Recom. It's a lot of words. But that still wasn't quite enough to do everything we needed to. So actually here it is running. Not real time, of course. So these are the kind of maps we get. And you see that like they have fine scales in certain parts of the graph, and then they go away because this is actually a real. So this is the 2-level one. We've actually run 3-level also. Okay. So these are the kind of objects we get as we run this redistricting. All right, so the problem, though, is that there's actually some natural temperatures in here. And if we really want good maps, so we want to be at low temperature, where things are really concentrated around the good maps. The problem is there's a lot of barriers then to getting between the different samples. So what we actually end up doing is, and since I'm running out of time, I'm gonna kind of be quick on this. I have like, what, 3 or 4 minutes? 5 minutes? Okay. So we use an idea called parallel tempering. So what we do is we run a whole bunch of different chains at different temperatures, and we swap between them in a way that so that every chain at each temperature is preserving the measure at that temperature. And by doing this, we actually, so we'll maybe run a chain with 40 different temperatures, and then we use another idea. So sometimes we eventually end up having run effectively at like 100 different temperature levels. And that's actually what and I should say that Feitfield and Inema had a similar implementation, a different idea, but related way of doing this. And so, so you run along it, so a given processor, so we're like running on 40 core machines. So we're popping along, and then sometimes we switch up to run at a different temperature, and we run there, and then we pop up and pop down. And so this is kind of following one processor doing as it's switching what temperature it's running at with other processors in the machine. Okay, so I mean, like I'm actually presenting in court multi-scale computation using parallel tempering. Right? So we had some other ideas. So all these things have been based on local reversibility. We actually tried to make some non-reversible samplers. So we generalized this idea of Hamiltonian Monte Carlo to this discrete setting and made some non-reversible choices, building on some ideas, some lifting skis of Diaconus, Holmes, and, oh shoot, I forgot the other author. That's horrible. It's being recorded. I'm so sorry. Just space. Neil. My God, Neil. Right? So, but I have to be honest, it didn't work as well. So I'm not going to tell you about that. But we've done some other things, like all things, to try an idea, and sometimes it's not as good as you really thought it was that night when you came up with it, and you were certain that it was going to be better than jam. All right. So now I want to slightly change something. So an interesting thing happened in this most recent North Carolina case. The court listened to all this, and they said, yes, 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 yes. We agreed that these were politically gerrymandered. Political considerations motivated this, choices of districts, and they had previously ruled in North Carolina that was unconstitutional. So they overturned the maps. But they said, we would also like, when you move forward, to submit maps that try to have partisan symmetry, that try to treat each party similarly. So we went through and helped kind of look through our maps and look for districts that, and so what this is this is when the party in power with the majority of votes gets this percentage of votes, how many seats do they get? The red curve is the Republicans, and the blue curve, which is now aquamarine on this projector, is the Democrats, okay? And there's a gap between them, and this was the map that was overturned. And then this was the map that was submitted by some plaintiffs to try to suggest that it be changed. All right, well, actually, it's a slight lie. The map was overturned, the legislature submitted a new map, and then it was critiqued. And because of this critique, because this one is much better, right? It treats the two parties much more similarly. The gap between these curves is much smaller. In other words, when you get 51%, they get similar number of seats most of the time. Here, there's a huge gap. So they actually threw out this redraw and had a special master come in and redraw the map for the courts. This is what our one from our state house looked like, and unfortunately they kept this map, even though it has this huge asymmetry. And what's interesting is even just a small change, there was one minority opportunity district which the legislature destroyed in the southeast corner of the state that reliably or had a good chance of electing an African American representative, and they destroyed it. And if you just put that one back in, it actually made it already much better. So the dotted lines are what happened if you restored that African American opportunity district. And this is what a much better one we could find in our own work. We could look through our samples and look for a good symmetric plan. So this is a little bit of a shift. Now we're saying, we're doing the other problem. We're saying, here's what we care about. Can you find a good map? So there's lots of interesting problems here. Okay, whoops. So lots of evolving subject, lots of work to be done. And I really believe this. Good math can be used to solve good problems, but often good problems lead to new good math. So this is a problem rich with possibilities to find new good math. There's been lots of people who have worked on it. So here's some of the group centered at Carnegie Mellon. They have some ideas of how to assess fairness of maps without worrying about mixing of Markov chains. These methods work even if the Markov chain isn't well mixing. So this was used in the landmark Pennsylvania case. There's actually, so in court, we actually did used a very sophisticated algorithm developed by Feifel Inema and their collaborators to actually enumerate reasonable sized districting plans in settings where we could enumerate them. And we actually presented in court this exact slide with the enumeration. So we did a very sophisticated recursive enumeration scheme, computational method, and to benchmark our results and say, look, our sampling methods are doing a good job on this problem we could solve exactly. And we presented that in court as a way to convince the court to listen to us. And there's lots of other people. I mean, there's lots of papers here. Some people using optimal transport to look at things, people using TDA, people using various ways to talk about what the map should look like. And so there's lots of different papers coming out all the time. And so let me just close by saying that another interesting fact about this, so first of all, let me thank my funding sources and the supporting sources. So the provost and the deans at Duke University have been supportive of this work, and the Data Science Institute at Duke, called IID, believe it or not, has supported this work a lot. But what's really another really nice thing, since we're one of our jobs is to teach and instruct, right, and to engage our students, is that this has been a fantastic, place to find great undergraduate and master's projects. And these are everyone who has undergrad or MS next to them, whereas either an undergraduate student, a UG, or an MS student. And these are all, starting with Christy Vaughn, who was the first one I told you about. These are all the different students who've been part of this. And this was a whole year-long undergraduate research class that worked on this stuff. And then I also have a bunch of other colleagues, some of them law professors, some of them mathematicians, who some of you may recognize that have talked to me about this over the years. And so it's really kind of a great place for lots of interesting things going on. And I'll just stop by thanking you again and just playing this movie because I like playing this movie. And so thanks a lot.
There's this massive time delay. Okay. You have an election on Tuesday. When they announce results, you have a lawsuit.
The lawsuits are actually beforehand. The lawsuits are when the maps are released. So the maps, this time the census was heavily delayed because of shenanigans of the Census Bureau. The census was released in August. We had maps by October-ish. Before that, we released some analysis saying this is what you should expect from these maps. And when those maps were different, we then analyzed the maps they released. Then that was November. By December, we submitted a brief to the court. By January, we were in trial. By February, it was overturned. By the end of February, we had new maps. And on Monday, the Supreme Court said they would not overturn the fact that these maps had been overturned. They let the overturnings rest. They would not intercede on behalf of the legislature, which was, so that was, sorry.
Yeah. So I guess the question is, part of it is, it seems like the right map drawn to take pictures there, whatever the best map and
Well, it kind of depends on, there's two parts to that, right? As I tried to imply, like maybe when you switch to deciding what you want the map to look like, you should make some positive other criteria to help separate the maps out. And the court actually said, we actually wish the legislature had said we want to have some kind of symmetry in this. So that was not part of the criteria the legislature continued. The court imposed that criteria in their ruling. So then we actually went back and didn't use our ensemble. We used a different method to it, right? And so right. I mean, but you could do that. So in that much, remember there was this whole discussion this year about the act in Congress about Fair Election Act, right? That never passed. One of the things it did in Luchin's later version of it, which was actually quite nice, is it said, here's some simple tests, and if it fails this, you immediately could overturn a map, or you could kind of have a fast-tracked overturning process. This doing it even at this speed required that I basically work through all of Christmas break. Yeah.
You have in your slide a 12 picture of Amanda packing crack.
Yeah.
Is there a person where this person is from? Is there like a person who is mastermind of this is how to
Mastermind of what?
crack.
Oh, I don't know. That's been going on forever, right? I mean, Governor Gerry was, right, gerrymandering should be Gerrymandering. Governor Gerry of Massachusetts was 1812. Right. I mean, it happens all over the place. It happens there are lawsuits in British Columbia about it in the past. There's something called Maggie's District, I think, in Vancouver. There was a local election district that had pretty much been gerrymandered to protect her. There's in Great Britain. I mean, I think we have the best track record of good gerrymandering, but other places do it too. It's fine. Right. Well, so the thing is, yeah. No. So, I mean, the way we treat it is we treat the data as a plausible voting pattern in the state of North Carolina. And then we ask, how do all these different maps react to this election data, and we actually never use data. Okay, I showed you some here, but actually in court we only use statewide elections. We actually never use congressional elections, or we never use legislative elections. And the reason for that is that there's a feedback loop, right? The way the election turnout happened was because of the way the district was drawn. And so we'd rather have just a statewide election where it was one candidate for the entire state. So that's what we use. And then we do something where we shift up and down that spatial pattern to create different plausible voting patterns at different statewide vote fractions. And the way I think of these is these are each probes that I probe this map with. And I ask that by looking at all these different voting patterns, I start to get an idea of how this map behaves under many different voting environments. And if it systematically behaves in a certain way under a certain type of voting pattern, then I should take note if that's not a typical behavior. Yeah, I mean, you might think that that's crazy. That's called the uniform swing hypothesis. What? Well, yeah, I mean, you know, we in the United States, there is no one answer to that question, right? We have 50 states and so many jurisdictions and so many court levels. But I mean, there's well-established work in the political science literature about how this uniform swing hypothesis is not such a bad way to, I mean, the thing to be careful about is I'm not predicting. I'm not trying to say this is what's going to happen in the next election. That's not what I'm saying. What I'm saying is here's a bunch of plausible voting patterns that have been used in the state of North Carolina that have happened in the state or are based on true things. Here's how this map behaves. Does this map behave in a strange way? That's what I'm saying. I am not in the business of predicting what will happen next. Yeah. So this is exactly what I was just saying. And I went fast, and I didn't give you all the details. So it's a great question, and thank you for asking, because you let me now fill in my talk. So what I do is in every precinct, I have a vote fraction. I move that vote fraction up or down by a 0.1% in every precinct, and I go up, and I move it down. Now, you may say, but what happens if in some precinct you go beyond zero, like a threshold? Isn't that crazy? So the first time I did this, I was offended as a mathematician. I first did this, and I set up some convex optimization problem, and I redistributed the votes so that it was, blah, 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 blah. You guys would all be really happy and impressed and stuff. And it kind of didn't make a bit of difference, that small correction. And trying to explain that in court obscured the point. So just a simple idea of shifting up and down it actually has been shown by political scientists to give rather plausible voting patterns. Yeah, you can't ask, does it predict the next vote if the vote for statewide swings? It might not, because these vote patterns are very different from election to election. And they depend on, like in North Carolina, I can speak about North Carolina. So, did the Raleigh-Durham area vote with Charlotte? Or was there an issue that divided the two main metropolitan areas? Did the rural Northeast, which is heavily Democratic, vote with the urban Democrats? Sometimes they don't. Did the West vote different than the East? One is the mountains, one is the coast. They sometimes align with each other, and sometimes they break with each other. Did the suburban parts vote with the urban cores? Sometimes they do, sometimes they don't. But we have lots of examples of different voting patterns where these different things happen. So you can ask, based on different coalitions that happen, how does this map treat them? And if when the coalitions that are important for one party to break a majority, all of a sudden are systematically disadvantaged, then you see it in these analyses. Does that help? Thanks, it was a great question, both of you.
When you define the distribution of temperature, did you change the parameters? Does that change
Yeah. So I think there's a great math question here. There's basically kind of a concentration measure, like some kind of insensitivity to changing these parameters, right? There's a great question about how to think about that as a high-dimensional sampling question, if you like to think about high-dimensional sampling questions. Hi. So, it's an interesting question to think about that, and I've wanted to think about it. I just haven't had time yet. What we actually do in court is we do what, this is in the trenches applied math. What I do is I fluctuate the choices I made. So how do I make the choices I start off with? I look at historical maps that we have from the state of North Carolina, and I look at the nonpartisan criteria, nonpartisan features of those maps. How many counties did they split? What was their typical compactness? How was the population fluctuations? Other things, right? And then I tune those parameters so that I'm sampling in the same area that from a nonpartisan point of view that look like the maps we used. And then I ask, now that I've fixed these nonpartisan criteria, is this map still typical? right? And then I fluctuate some of those parameters, those weights in front of those functions, up and down some percentage. And I ask if the qualitative results that I get change. And I always present that in my reports and sometimes in court, depending on how much time I have. I try to present sensitivity analysis in court.
Go ahead, Eric. Yeah.
I wanted to ask, when you run this algorithm for a long time, it looks like you start with an initial condition,
Yeah.
which maybe is the last map or maybe not. How much drift do you get away from that initial condition?
A lot.
And with your temperature thing, are you sure that your full ensemble?
Yeah. Okay. So sure is a really hard word, right? There's sure like mathematician sure and reasonable sure, right? Right. So reasonable sure, what we do is we start with a system to generate a whole bunch of random initial conditions. So then we study how independent chain starting from those different random initial conditions behave. And then we look at we pick some of these projections onto these marginal distributions. So that gives us like 14 marginal distributions from each map, from each ensemble starting from different initial conditions. And then we look at the total variation distance between those distributions pairwise over time, and we wait till the worst case pairwise distribution is reasonable, has dropped down significantly, so they all start to look the same. And then we also compare the beginning of runs with the end of runs. We take a burn-in chunk out, we look at the middle part, the end of the part, we look at how the correlation, we do all those kind of tests. So kind of standard Gelman-Rubin statistics and stuff like that. Yeah, so I mean, I didn't tell you about all that, but yeah, I try to be a careful applied mathematician and check all those things as best I can. I mean, when I'm doing it in 7 weeks, it gets hard.